And you probably now have a good idea who everybody is. So hello and welcome to the fifth webinar of the Preparing for the PAT course 2023. My name is Kat. I'm the Physics Access Officer at the Department of Physics, and I run most of our programmes for our secondary school students. And that includes all of our staff to support people interested in studying physics here in Oxford, but also more widely. We prepare people for lots of different courses. I would like to take this chance to let you know that this session is being recorded and will be made available to you tomorrow. So everyone who has followed this link is also part of our email list. Your links will come through to watch this tomorrow. Quick reminder of housekeeping rules for those of you joining on Zoom. You will be able to use the Q&A and the chat a little bit later in our session. I will switch that on and I will let you know when that's ready. You can access the chat to share thoughts, and you can use the Q&A to share questions specifically for Rachel, but please keep it polite, keep it kind, do not share any personal details or information, and if you want to answer questions specifically, keep those to the Q&A. But let's get started. Enough of the admin. So we've had lots of new joiners since our last session back in July, and I'm going to start with a reminder of what the PAT is and what this course is. I won't take questions during this section. I am going to talk for a few minutes, and if we have time at the end. So the first things first, the PAT stands for the Physics Admissions Test. It is the test that must be sat by all candidates for physics, physics and philosophy, engineering and materials science at Oxford University. Your result on the PAT forms part of the information which the admissions tutors use to decide who is shortlisted for interview. To sit the PAT, your school must register as a test centre and you must be registered as a candidate. In the vast majority of countries this year, the PAT will be in a hybrid format with questions on screen and a paper answer booklet that will be scanned and returned to us for marking. The online test will include a built-in on-screen calculator, and there is a trial of this online now so that you can practice with it, and I'll share links for that. This webinar is part of the PAT preparation course, and we run this on behalf of all of the subjects who require the PAT. The Preparing for the PAT course is a series of 8 webinars. This is our 5th webinar, along with problem sets and summer assignments that we hope will provide you with all of the information that you need to take the PAT, help you prepare for the PAT, and be confident going into interviews if you're shortlisted. The timetable that you can see on the screen at the moment is at the bottom of every PAT email. So those of you who have had our emails will have seen this at the bottom. We always highlight which week we are in so that you know where we are and you can follow our progress. In each session, I'll fill you in on any updates or news, such as the fact that registration for candidates is now open. You guys can get yourself set up. You can see that this is our 5th webinar. We're highlighted in the yellow colour. And today is a teacher-led problem-solving webinar with the lovely Rachel, who you have already met. Rachel also joined us in the very first session. So if you haven't had a chance to look back on any of those sessions, it might be a really good chance for you to do that afterwards. Rachel led an amazing session on general problem solving. So that might be really helpful for you. All of our previous sessions, if you are wondering where to find them, are available on our PAT course materials page. And there's a section of it up there so you can see what it looks like. Right at the top, there's an introduction to physics problem solving, which looks in detail at some of the contents that Rachel discussed in our first webinar. And then underneath, you'll find all the links related to the webinars. And it's set out really clearly. So click here for the problems used, click here for the recording, click here for problems to solve in advance. We update that after every session so that you can find everything that you need. Finally, just a quick reminder that all of the information that both you and your school need can be found at this page. So on our main university website, this is the one that is updated most quickly with any new information. And again, this is shared in all of our emails. It's the most up-to-date page, it's the one to check. It's also got an FAQ page, which is really helpful. The most recent update is that both registration for schools is open, so your school can register as a test centre, and candidate registration is open, so they can register you. Now, this might sound like a really big deal and like a huge thing that you need to organize, but trust us, your teachers are used to this behind the scenes. They will do it for all of the big examinations that you need to sit and for any other admissions test that any pupils need to sit. Your school will have had all of the details for how to do this. Again, there's a really good FAQ page. You don't need to worry about this too much, except bugging your school to make sure that they've done it and that you are registered as a candidate. That one is completely on you. If your school are unsure, mention to your teachers that they're welcome to contact us or go through the links that you can see on the screen for any more information. You've still got a good couple of weeks to go until the end of the month, so we should be able to get all of you registered. Very quick note on that is that if you're applying and you do not attend a school, so maybe you've taken a year out or something like that, you can apply to sit the test at a school or a venue that's a registered test centre but is near you. And again, you can do that through the admissions portal. And very last but not least, the test format, which I mentioned earlier, it is a new one, this hybrid format, and the mock-up of that format is available now. It's not as big a change as you think. The questions are really similar. The syllabus is unchanged, but even though it's not a big deal, we know that a lot of people, this is an important thing for you. So we've made sure that the mock-up of the test is up there. You can try it, you can trial that calculator. And that brings me to the end of my quick PAT introduction and update. I hope it was really helpful. If there is time after Rachel's session, I will take questions at the end. If not, our session next week will be being run by two of our undergraduate ambassadors, and I will make sure we have time for a Q&A session then. You can also contact me by email, which you receive on all of your PAT test emails. So loads of ways to get in touch, lots of ways to solve problems. I am now going to hand over to Rachel. I will share in the chat with you a link to the problems that Rachel is going to be using today, and I will make sure that our Q&A and our chat sessions are enabled. So we are ready to start. Rachel, over to you. Thank you so much.
Hi, good evening again, everyone. Just as a reminder, if you could put questions for me in the Q&A, we've got quite a few screens here, so if it ever looks like I'm not looking at you, that's the reason why. If you can put questions for me in the Q&A, that would be great, and I'll deal with them when I can, or later on in the session if that's appropriate. And answers as they're coming in, I think you can send it to hosts and panelists. That's probably a good way until we get towards the end of the question. I think that must be, you must be able to do that. So answers, you can pop in the chat to hosts and panelists, I think. And then when we get towards the end of the question, you can post them to everyone, because that's good for you to all see your final answers, okay? Because you might put an answer and then want to change it a little bit. So answers in the chat, Q&A for me or Kat over time. So I will share my screen now. And just as a reminder, if you need any tips or hints, there are some tips and hints in the booklet that Kat has just sent the link to, but I'll be giving you some little tips and hints as we go on. And this time we've chosen a really specific topic. So we have chosen waves and optics, because I've taught you before, if you've done the session before, you can go back and study it, problem solving techniques. And now we're going to apply them to a specific area, which is waves and optics. And if you're anything like my students in year 13, it's the kind of topic you like to neglect. So make sure we can practice these, and we'll be looking at this today. So just a little warm-up question. Not one that I made up, but there's a really good resource out there called Next Time Questions. You're welcome to go and look at it. Some teachers use it. Have a read, and in the chat you can write your answer to host and panelists when you think you have it. I will sometimes mute myself and maybe turn off the video. It gets a bit tiring if it's non-stop, but I am still here. So it's so great because I think I've seen every single possible answer there. So it's a real question that's making you think. Okay, E is seeming like a popular one so far. But I think I've seen every answer, and I've seen multiple people saying the same answer. So thank you for sharing that to hosts and panelists. We won't do that with everyone today because it's all just a letter. I think the most popular probably was E, but let's just have a look at that. Okay, and rather than me explain it all in detail, it's kind of a written answer for this one, which is a bit different to some of the other questions. Oh, sorry, technical hitch. Okay, so the correct answer is actually B. So have a good read of that and think about the idea of the ray diagram you would draw. Okay, have a good read rather than me repeat it. So it's really important that mirror is half of your height. And I think lots of you are thinking about your life experience with mirrors and how you can move away and still see yourself. But the key part of the question there was being able to see a full length view of yourself, a full length view. So if you think about the only way you can see the top of your head is if the mirror, if you look above the distance, halfway from your eyes to the top of your head, that's how you'll see the top of your head. So we are using, sorry, I'll turn the laser pointer on so you can see where I'm looking at. So if you look above at a distance halfway above your eyes to the top of your head, you'll see the top of your head. So using the law of reflection, that's talking about this section of the diagram here. Okay, so the mirror is going to need to hang just above the top of your head. And then the minimum size for the plane mirror needs to be half your height. And that is because that's the only way, using the law of reflection, so angles of incidence being equal to the angle of reflection, that's the only way you can also see your toes at the same time. So we're using the idea of ray diagrams and the law of reflection there. So a bit of a challenging one, that's why I like this question so much. And one more warm-up question, have a good read of that. Okay, have a good read of that. And again, for this, because multiple choice, pop your answer to hosts and panelists when you're ready. The options are above, below, or directly at. And it's quite common in physics to see a question like this. But this time the question's with a laser. So does that change your answer at all? So we've got above, below. Lots of people saying, what's the most common at the moment? So it's a laser sphere, not a normal sphere. Great, loads of answers. Thank you, Freddie. Thank you, Edith. Thank you, Corin, Khalid, Zara. So we've got a mixture above and below. The most common recently has been, I say above, has come out as the most common. Now, interesting. Let's have a look at the answer. So if you said that Huey should aim directly at the fish, that would be correct. Because if he was throwing a sphere, he'd have to compensate for the refraction of light. Because the visible light that he was seeing, his brain would then think that the fish were here. But that was the challenging part of the question. He was actually using a laser sphere. So the sphere is actually a light beam itself, and the light path is reversible. So we'll go from A to B along the same path that it takes from B to A. So that's why it's so challenging. It's why animals like bears are actually adapted to hunting for fish under the water through a lot of evolution over the years. When usually with our eyes, we will see the fish as a virtual image higher than the reality due to refraction of light. But the trick in this question was it was about a laser sphere. So you actually aim exactly where you see it, exactly where you see it. So if you like those questions, this website, Next Time Questions, has got it for every single topic, but that's just to really introduce you to some of the ideas. And I haven't gone into detail yet. We'll go into detail about reflection and refraction in this topic, but with some more challenging concepts. So remember, with the other questions we're looking at today, if there's anything you get stuck with, there are some extra hints in the booklet, but don't look too far ahead. You want to push yourself in this session. And I'll also show you how to start questions well. So it's really good that we've got paper answer booklets in the exam, because that's what you should have in front of you now, a sheet of paper so you can sketch diagrams and complete the mathematics that you need to. Also, with calculators, using the calculator should be the final step in these questions. So you've got a new online calculator in your PAT test, but that's absolutely fine, because the final step should be when you use the calculator. Do the problem solving without the calculator until the very final step. So advice, learn your formulae for all your PAT topics. I said this in the last session. Check your syllabus for definitions and equations that you have to learn. There's more that you have to learn than in A-level, like off by heart. Always draw your own ray diagram, even if you're given one. That's actually even better. I didn't update that tip, but now you've got paper to work on. That's what you need to do. Always label your angles, because they won't be drawn to scale on your exam paper, but you can do a sketch where you label your angles. And then don't forget to use simple geometry rules to calculate your angles. And don't forget Snell's law and total internal reflection rules. So we'll be using those today. So get that brain whirring about those. And remember, we're going to use this a lot today. We make an assumption in physics that refractive index of a vacuum is 1. And we can also use that often for air, okay, unless otherwise stated. So you don't need to read all the detail here, but I copy and pasted from the syllabus the bits and pieces that we're kind of reviewing today with a few examples. So we're looking at reflection today, and you've got the law of reflection there in the syllabus. We've got refraction, where we've got Snell's law. We've got total internal reflection and the idea of the critical angle. And you need a qualitative understanding, so that means without the numbers and equations, of how interference, diffraction and standing waves can occur. So all of these are year 12 or even GCSE topics, but obviously you're going to be applying them to challenging questions. So the first problem, another multiple choice, so let's send the answers just to hosts and panelists. Have a read and see what you think here. Read the question carefully. Remember, if you have questions, pop them in the Q&A, please, even if it's questions about the PAT tests, and Kat can answer them there.
Yeah, absolutely, Rachel. I am moderating the chat and the Q&A, so anything that you need answered, pop them in.
And got a few answers coming through, but I won't share what they are yet. Thank you so much to everyone for participating. Just make sure you're reading the question carefully. It's a beam of coloured light. Okay, it's a beam of coloured light. So, for example, it's going to be one colour, potentially red. It's a little bit different. This question's not about the dispersion of white light, okay? And what always helps is where you've got a light ray entering a different medium, we always draw a normal at right angles to the surface. So do a quick sketch. Good, I think most people are on the correct answer so far. Okay, and the answer is not C, because light refracts when it enters a different medium. Okay, so it slows down when it enters a different medium, and in this case it will change direction. So it rules out C. It's not D, because it says it is a beam of coloured light, so it doesn't depend on one colour. Sorry, it doesn't depend on the colour, because it is one colour, and refraction will occur the same for all colours of visible light, or all areas of the electromagnetic spectrum. So we're talking about the coloured light at the prism. Draw the normal on, as I've just shown. And we should remember that as light enters a more dense medium, it will slow down and bend towards the normal. The question was only about it being at the prism, so we don't actually need to worry about it leaving. And then the correct answer is B. So huge proportion of you got that correct. Well done. Fantastic. Okay, so the next question. Have a good read of this one. So for this one, it might be quite hard to pop the answer in the chat bar. We'll see how we get on. But what I'd like you to start by doing is, once you've read the question, draw a diagram. Draw a diagram to represent it. Okay, so draw a diagram, and just some key details. Remember I said with problem solving, you've always got to break down the problem. It's really important that the light is incident from a vacuum onto a medium. So medium is just like another word for material, different material. So from a vacuum onto a medium at an angle of theta to the normal of the boundary. Probably should have underlined the word normal as well. The refracted and partially reflected beams happen to form a right angle. When they give you an information like that, you're going to need to draw it on the diagram. So hopefully you've done a quick sketch. Okay, and your sketch hopefully looks something, don't forget to use a ruler, like this. The only thing I haven't got on there is my arrows. Okay, the only thing I haven't got on there is my arrows. So, oops, sorry, shouldn't be going to the next step already. So you can see there, I've got a diagram which shows my incident ray, oh, that's a dodgy arrow, but you get the idea. My refracted ray into the medium, I'm just going to call it M for medium, this is V for vacuum, getting creative here. And then we can see my reflected ray, all the information. And actually at any interaction between two mediums, there will always be some reflection and refraction. Sometimes students forget that. So we'll look at this information in a little while, but I've got my incident ray labeled, my refracted angle of refraction labeled as well. And remember, the angle of incidence, angle of refraction is always measured from the normal to the ray. Okay, good. I've got lots of people that have simplified this already. Well done, Diane, Yitian. Well done as well, Henry. Yeah, loads of correct answers coming in. We'll try not to send them to everyone until right at the end. Okay, and then some people are heading that direction. So I'll add the extra details that I know. So I know the vacuum. I make the assumption, because it's not in the question, that it has a refractive index of 1, and the medium will have a different refractive index. So we need to learn Snell's law for the PATs, which is given here. We know that material 1, so that's always where your ray starts, that's the way I always work it, has a refractive index of 1. So straight away, we come to a slightly simpler version of Snell's law. We then need to rearrange and substitute in for the angle of refraction. A rule we can use here, because we have that 90-degree angle where my laser pointer is that sine 90 minus theta is equal to cosine theta. That's going to be useful. You can see that the angle of refraction is equal to 90 degrees, the angle here, minus theta, because we have angles along a straight line. So we know that theta plus the angle of refraction must be 90 degrees as well, for example. But that's how I broke this down here, to get the angle of refraction being 90 degrees minus theta. And when we worked that all the way through, and I saw a lot of correct answers coming in, we rearranged to make the refractive index of the medium the subject, and we get sine theta over sine the angle of refraction. We can substitute in that we found it was 90 degrees minus theta. We know, using our trig identities, that that's cosine theta, and then it simplifies in a really lovely way to tan theta. So well done. Even if you did some of these steps along the way, that is excellent. And if you got to that final answer, that is as simplified as we can make that question. So the unsaid information in that question was the idea of the vacuum being a refractive index of 1, and remembering to use our trig identities and geometry along a straight line, or knowing that theta plus the angle of refraction is going to be 90 degrees. using this shape here. So next question, a little bit longer, so you will need some time to read it. The first thing you'll need to do is make sure you've got some definitions. So something that we really need to make sure we have clear definitions for those phrases. And you're encouraged to use a diagram for your answer. But anyway, I'll let you read it. Make sure you do write down definitions. My students try to avoid that. So write down the definition and we'll check that in about a minute. Okay, so write down the definition, commit pen to paper and add a diagram to help you define it. 1 minute. Maybe 2 minutes because you've got quite a lot to read actually. 2 minutes. Okay, so if you're feeling brave, write your definition for either total internal reflection or critical angle in the chat bar to everyone. How do you define it? And I'll show you how we define it with diagram shortly. Thank you so much for the answers so far. Keep them coming, okay? Definitely lots of parts that are really correct there. Well done. Well done. Thank you, Alicia. Thank you, Coran. Thank you, Remy. Yeah, you can send them to host and panelists as well. Absolutely fine. Sorry, I've got a fly buzzing around. Well done. Okay, so can we see if we can get any definitions for critical angle? We're all going for total internal reflection now. One thing to clarify about total internal reflection, we can't just say, for example, that the light comes back on itself, because that would be a bit like reflection at 90 degrees from a mirror. The light's coming directly back. So we'll be really specific with our language in a second, but we're all getting the right idea that it's to do with the difference in refractive indexes between the mediums. Okay, we've got some good ideas for critical angle. Thank you, Elliot. The maximum value that angle of incidence can hold. And one thing to be careful is actually the minimum angle for critical angle. Okay, finish the sentence you're on if you're typing something, and we will check. So this is the kind of thing where we've got to really get our definitions for both A-level and the PAT. Okay, so the level of detail we're looking for, total internal reflection is the complete reflection of light within a medium. It occurs if the angles are greater than the critical angles. So you actually need that in the definition. It can only occur when a light ray passes from a more dense to a less dense material. Or you might have used the idea of a higher refractive index to a lower refractive index. That's fine as well. So critical angle is the minimum angle of incidence at which rays undergo total internal reflection. So they're linked. They go hand in hand, these definitions. And as a diagram, we have two diagrams here. So the black ray diagram, we've still got a ray, a pair of rays here obeying the law of reflection, but they are performing total internal reflection because we have a refractive index that's higher for a more dense medium. That light ray is approaching a less dense medium, so the boundary to a less dense medium, and the angle of incidence, so where the laser pointer is now, is greater than the critical angle. So that's why that ray will totally internally reflect. But this ray, the light blue one, that's traveling that's traveling with an angle of incidence at the critical angle, that is the minimum angle of incidence at which rays undergo total internal reflection. So this still counts, but when it's traveling along the edge of the optical fiber, that was what the angle of reflection, sorry, the angle of refraction or reflection, depends how you look at it really, along the edge of the optical fiber. Anything just to the left of this, greater than the critical angle, will be total internal reflection. Okay, so the next part of the question, we are here. We need to derive an equation relating the critical angle and the refractive indices of two materials. Specifically where the refractive index of the second material, so a bit like in this diagram here, is less than the refractive index of the first material. Can't remember off the top of my head, but I'm pretty sure that's an A-level derivation as well, or it's important and useful to know. But just as a reminder, you're going to need to use Snell's law to help you work that out. So I can see some people are carrying on with that now. So yeah, any answers you type for the next part, please send to host and panelists for now. And we are looking to derive an equation relating the critical angle and the refractive indices of two materials. So actually none of the question yet is about this part down here. And that's why I've not really reviewed the top part of the question yet. So you've got to go into the question and look for what it's asking. So here's the diagram that we drew. And remember, we know the condition that we get total internal reflection if the angle of incidence is greater than the critical angle. We need to do it from the question. I've drawn out the key information and noted it down. So the N2, the refractive index, remember N is a symbol for refractive index, is less than N1, and we have Snell's law. So writing those down as well. Well done, got some answers coming in. You can look ahead at the question in the pack as well if you want to work at a faster pace. Try and do it without the hints if you can. And then we know from the diagram that at the critical angle, that's why that information is going to help us with this derivation. Theta2, it doesn't refract through, it refracts along the optical fiber, and the angle of refraction there is given by my red right angle, which is 90 degrees. So that's extra details. We know that the ray would be along the critical angle at that point. So I'm kind of talking about the blue ray in this derivation. So we end up with sine 90 being involved, with sine of the critical angle equals N2 over N1. Yeah, so well done. Whenever you see 90 degrees involved, that's going to be useful when it comes to trig. So there's our derivation, and important, helpful at A level as well. Okay, so coming back to the question, if we come back to the first part, lots of questions at A level and in the PAT are to do with optical fibers, because that involves total internal reflection, but also refraction. And yeah, anyway, we'll talk about that in a second. So we are looking here at an optical fiber because it's usually made of two materials, a core, so this is where my pointer is now, and the cladding, which is around it, and that's in the A level course as well. The cladding usually has a lower refractive index than the core, and that's why they work, because they work through total internal reflection. So this is the important part here of the question that's going to be the most challenging. Have a read of that, use the equation you just derived, and have a go at drawing a diagram for this end of the optical fiber. That's a bit of a clue to help you, okay? Draw a diagram and start labeling what you know. So I'll let you read the question a little bit more. Draw a diagram and label what you know. Yep. Remember that the refractive index of the core is greater than the cladding. That's going to be important because then we can use the critical angle equations. You could also draw what's happening to the ray in your diagram. So you are using this, but you're going to have I have to add more details. What's happening to the ray as it enters the core? Okay, so this ray is out here in the air, and then it's entering the core of the optical fiber. This is how sort of most of the time the internet's getting to our house and things like that, useful communications. And then at the edge of the core, that's where total internal reflection happens. Or we can make an assumption to do with the critical angle. So as a little clue, there's refraction happening to the ray as it enters the core. And we're going to have to make an assumption that for the ray to get transmitted, it hits the core cladding boundary at the critical angle. So with its angle of incidence at the critical angle. So I'll give you another 10 seconds to go with your diagram, or you might be ahead of that. Great, so some of you have given me some answers. Kitan, I think you can simplify it a little bit more. You're very, very nearly there. And Tejas, I think you have the correct answer there. It's always hard to see when you've got to type it in. But carrying on, if you are happy with your answer, you can carry on with the questions in the pack from the link that Kat said. But otherwise, here's the diagram that I would draw. So we're taking this section of the diagram of our optical fiber, and I'm showing that the ray approaches at an angle of incidence that I do not know, but it will refract towards the normal. So see, this ray has bent towards the normal. And I've labeled this angle here, and I'll review why I know that it's 90 minus the critical angle in a second. I'll talk to you about that in a moment. Here, I know that for my ray to transmit, I can't really draw it all reflecting billion times on total internal reflection, but to have a great amount of transmission, it can just pass along the core and cladding boundary. And that would be the ray approaching along the critical angle. I've labeled very clearly, you must always do this, my refractive indices to make it really, really clear. And therefore, the reason I know that this angle here is 90 minus the critical angle is because multiple reasons, but the way I would do it is angles in a triangle, 180 degrees. I've got this as 90, I've got this as a critical angle. So this one must be 90 minus the critical angle. So I remember, always keep that in mind, that this fact must be true for this optical fiber, otherwise it wouldn't work. And we're going to assume the transmission is at a maximum. Oh, I think I actually said that at the question, when the ray meets the core cladding boundary at the critical angle. So at A, we know this to be true, what we just derived. So funny enough, the question led us there, that sine of the critical angle equals this. And at B, because we have refraction, we know that Snell's law needs to be applied. So with everything in the diagram and those two equations to use at A or at B, so at A, you're using this equation, at B, you're using this equation, use the information from the diagram and try and make substitutions to make it specific for this question. I'll just check a few more answers that are coming in to host and panelists. Thank you. Excellent. So Henry, I think that looks right. I think, who else have we got here? Make sure you do use your trig rules in this. Okay. Alice, you're nearly there. I think you can simplify it a little bit more. Okay, I'll show you the next steps. Hopefully that timing is okay. If timing's too fast, let me know to host some panelists as well. That would be great to hear. So substituting what I already know from the question, we know that the ray is at B, so we're dealing with B first. The ray is starting off in air with a refractive index or a vacuum. I think it's air from the question, refractive index of 1. We know we're going to call this the maximum, that's what we're trying to find out, the maximum instant angle for transmission to occur. And then at B, so this part here, I know that my angle of refraction is 90 minus the critical angle, because I worked that out from the triangle rule. And I'm going to call that n core. Then I also know, oh yes, so I've added on S, sometimes I need to look at what I've already written. I also know that sine 90 minus theta equals cos theta. So that's probably going to be helpful. Okay, so I'll substitute that in straight away. And so the one can simplify. We end up with n core cosine theta. And then for reasons that will become clearer, actually, I won't mention that now, but we're going to head here for reasons that will become clearer. Because sine is going to be more useful again, but I can't work with sine 90 minus theta when I have sine theta up here. So using trig identities, using sine squared plus cos squared equals 1, I can replace cosine theta of the critical angle equals 1 minus sine theta c squared. Sorry, I forgot squared. And you square root the whole thing. So you know your trig identities hopefully, but I can see up here, I've got sine theta of the critical angle. It's not going to help me if I leave sine 90 minus theta c. I have cosine theta there. There might be another route to do it, but this is the route I've chosen. So then go back and use equation A for the critical angle. See if you can do the next steps if you haven't already. I'll check what's coming in. You can look ahead on the pack at the next questions. So let's see. Freddie, just check your, I think it would be your simplification there. You're very close to the correct answer. Okay, and remember, we are trying to find the maximum instant angle where the ray meets the course and cladding. So that's theta max. We're trying to find theta max. So make sure theta max is a subject at the end. Okay, and then I'll show you the final step. Most people that are submitting answers are pretty close at this point. Okay, so using equation A, sorry, I tried to just edit that a bit at a time, but it didn't work. So here, if you're using sine theta max for n core from before, the highlighted part of the equation, square times multiplied by square root of 1 minus, this is where I've substituted in the critical angle. So this is not as simplified as we can make this. If you multiply out what's highlighted here in this bracket and what I'm pointing to with the laser pointer, you can eventually simplify it as far as this. And lots of people were sending this in the chat bar in the end. Some people were forgetting square root, and some people were forgetting that we just need to do one final step, because this is with sine theta as the subject. You need to make theta the subject. So arc sine, and then that same square root. And that is as simplified as we can make it. Yeah, well done. A few people did the final step in the chat bar just then, sending it to hosts and panelists. Thank you very much. So that is as simple as we can make that. There might be one different step you could take along the way, but that's the route I've taken. So don't forget your trig rules. Sine was more useful in this, this route. You can always tell me in hosts and panelists if you did it a different way. It's always interesting. And we've got geometry rules as well with the triangle. So I think we finished that question. Question solved. Well done. Here is our next question. So again, an optical fiber question, because these are the ones that are challenging. So I'll give you some time to read it. And you, of course, are going to need to draw a diagram. I'm still here, but I'm going to turn the video off while you draw the diagram. Okay, hopefully you're making some progress with the diagram. And I just wanted to point out this idea. So sometimes you're going to get thrown new rays, that too as well, but new words. And I'm not sure whether you all have seen this before. But the meridional ray, hopefully I said that right, is a ray that passes through the axis of an optical fiber. Okay, so that's why it says that, or that's what alternatively can happen, because the optical fiber can travel directly down the middle, or alternatively, the meridional ray can pass through the axis of an optical fiber. So it can pass to bounce off the wall at least once. And then the question here, there's really important information here. It says, yet it stays in a single plane. So all of that's going to be really important for your diagram before you even start doing any of the geometry. Again, this whole idea, the minimum angular ray can bounce out is controlled by the critical angle. So we've got details of the refractive indices as well. So those are all clues that we're definitely going to need to use Snell's law. We're definitely going to need to use the rules for critical angles. And we've got the length of the optical fiber as well. So these optical fibers are really long. That's why they're so useful in communications and quick. So we are using light. So first step, we want the minimum angle. We know that this is the case. So we are going to need to use the rules for critical angles. So my diagram looks like this, where I have a ray. We're not worried this time about going from air into the optical fiber. This question is about being in the optical fiber. Okay, so light can travel straight down the middle. That's what this question's about. Light can travel straight down the middle of the optical fiber. Or it can be a meridional ray. And we don't actually need to be concerned about multiple reflections to calculate the maximum path length, because you can actually make a really straightforward assumption. Because yes, you probably learned about total internal reflection where it reflects lots and lots of times. We don't need to, because the question states that the ray is remaining in a single plane. Also, it wouldn't be traveling along the critical angle at an angle to the normal of the critical angle. So we need to use that assumption that the maximum path length remaining in one plane is one that will occur when the angle of incidence equals the critical angle at the cladding, and probably at the far end of the optical fiber. So this is like at the far end of the optical fiber. I haven't drawn the whole thing, I've just done a quick sketch. So it's remained in a single plane. So that ray has remained in a single plane, and towards the far end of the optical fiber, potentially has hit the optical fiber at the critical angle. So that keeps the ray in the single plane, because you need to make a few assumptions to do these challenging problems. So then, I'm not sure if everything changed color for you, but it is here. Anyway, hopefully that's okay. We have we clearly state the refractive indices and make a note, and we're making that assumption that the maximum path length occurs if the ray is hitting the cladding at the critical angle. So straight away, we can use our rules, our trig rules for critical angles. So we can get the critical angle and redraw what's happening with our two different rays. So when we redraw the diagram, this is the meridional ray traveling an extra length. So a difference in the path difference. So we always talk about path difference with in waves topics, and especially to do with optics. And this is the length of the whole optical fiber. And remember, the start of the question says that light can travel down the middle of the fiber. So that light travels 1 kilometer. But this meridional ray, we've modeled it as hitting the boundary between the core and the cladding along the critical angle, and just refracting along the last little bit of the optical fiber. So we're modeling that. That is the extra length that that meridional ray will travel. So knowing that the critical angle we've just calculated from the refractive indices is there, calculate the difference in path length. And lots of correct answers starting to come in. I think I've got a few questions, so I'll try and look at those as well. And we're really just interested in that point of almost kind of total internal reflection where it's the ray is traveling along the critical angle. And we're not really worried about knowing exactly where it started off here, because the light rays are being sent, all these photons are traveling along the optical fiber. And we're just interested in two different versions of the rays. There's obviously loads of them in between, but the question is asking about this ray, the meridional ray, and this ray. One plane. So I've got a question in the Q&A about one saying the same plane. That means we're just in one plane. So if you think about X, Y, and Z, the meridional ray is traveling one plane if it stays going in this direction. And it depends where you resolve it. But if I'm just looking along this plane, that's one plane. Okay. The separation between the walls is not needed. That's another question in the Q&A, because we don't need to know exactly where this ray started off to solve. We do know it started at the same, probably the best way to explain it is it started in the same place as the ray that goes all the way down the middle of the optical fiber. So we don't actually need to know how wide the cladding is, because we know that if this meridional ray hits the boundary at the critical angle, at the far end of the optical fiber, it will just refract along and exit. You'll be able to get that data at the other end, that information. So you don't really need to know the width of the optical fiber to be able to solve this. You're solving this using laws of refraction, laws of total internal reflection. You don't need to know the width of the fiber. So hopefully that answered that question. So hopefully, I think most people have tried that so far. The maximum path length therefore ends up being this. So the maximum path length of the meridional ray would be this. So this is our maximum path length of the meridional ray. And we know that the length of the other ray that goes straight down the center of the optical fiber is 1 kilometer. 1 kilometer. Okay. So if you've got an optical, an alternative method, send that to hosts and panelists, okay, because it's good to read about them. But we will move on to the next part of the question, part B. So this question moves on to wanting to calculate the time difference. Actually might move on from this question quite quickly, because I want to show you, we're running out of time relatively quickly. And then we'll give it a good start. We'll see how we go on. So next, we're moving from path difference to time difference. So you have to think about what you already know, assumptions you know about the ray. And then the final question asks you about the maximum rate at which information can be sent. Remember, if you have questions, put them in the Q&A. So I just had a technical problem, but I think it's all okay now. Okay, and while you're answering that next question, I'll just go back. So where we got this triangle here is, sorry, I'll turn the laser pointer on, this is the meridional ray. Okay, so the meridional ray is one which bounces off the walls yet stays in a single plane. So this is the meridional ray as well. I just did a quick sketch here without much detail, no distances involved, just focusing on the angles. But then when I want to calculate the difference in path length, because the question says it stays in a single plane, remember the assumption is that the maximum path length occurs if the ray hits the cladding at the critical angle, but also towards the end of the optical fibre. So I'm modelling that this meridional ray, the question also says the optical fibre is 1 kilometre. So the whole optical fibre, which obviously I've drawn a really short version of it here, is 1 kilometre. So that's why I know that the meridional ray will eventually go and hit the boundary at the critical angle, and the overall length of the optical fibre is 1 kilometre. Okay. Then using sine, I've got my opposite length here. I've got my hypotenuse. Yeah, sorry, I had a mental block there. And so that's why we're doing sine of the critical angle is equal to the opposite over the hypotenuse, which is my mystery path. I don't know the maximum path length that the meridional ray can take. And then when I make the maximum path length x the subject, I end up with this path length in kilometres. That's the maximum path the meridional ray can take. So square in time, Corin's just asked a good question in the Q&A. So remember, keep your questions there. Square in time, well, hold on, where's the question gone? It's a bit like it's a digital signal. So they don't mean that we're squaring time as like raising it to the power of 2. They mean, the question means we have a digital signal, which is how optical fibers work. 1s and 0s we're sending, and I think that will help if I sketch a little diagram of that. So I will go on to the next part here. Sorry, having a technical hitch. Right, we'll just move on here. Oh no, where did it go? Okay, so first of all, if we're going to find the time difference, we need the path difference. So using our information we calculated here, the maximum path and the length of the optical fibre, we know the path difference will be 2.67 metres. So getting that into metres. We therefore know that the time difference, just going back all the way to distance equals, speed equals distance over time. We're not using speed, we're using the speed of light, c, dependent on the medium. Oh, hold on, can you still not see a screen still? Let me just see. Oh, hold on a second. Okay, hopefully that's okay. Let us know, hosts and panelists, if that is not okay. But the refractive index and speed are related by another equation we need to learn. There are a lot of equations in this topic, where refractive index is the speed of light over the speed of light in the medium. So the refractive index of a material is the speed of light in vacuum, sorry, forgot to say that, over speed of light in the material. So when we change the subject, the speed of light in the material, or the medium, we know that refractive index of the medium given in the question for the core is 1.5. So that's going to be useful in the next step as well. And we know the speed of light in a vacuum is 3 times 10 to the 8. So using our difference in path length, the time difference between those two rays is the difference in path length. So it's the time difference between one arriving and one moving on. Okay. Divided by the speed of light in the medium, where we substitute in c over 1.5. And we should end up with a time difference that is stated there. So very, very small, but these things are important. These things matter. Yeah, so no diagrams, we're on calculations now. We're using the path difference from part A, because you had the path length, so the path difference between the original ray down the center of the optical fiber and the meridional ray is given here. So that's the path difference. And then the time difference, we need to use the refractive index to help us calculate the speed of light in the medium. We know this value here, c, is the speed of light in the vacuum, because that is a part of a definition of how we calculate refractive index for different mediums. And that should be the time difference. So I'll move on now. If you've got any questions, remember to put them in the Q&A. So this was the part that I had a question in the Q&A. If square in-time pulses of light are used to send information, calculate the maximum rate at which information should be sent. So the shape, basically, this is not a perfect diagram, but that's a square set of pulses. It's sending a digital signal, ones and zeros. The minute you see the word rate, that question there, and I always teach this to my students, year 7 onwards, rate means per unit time, usually per second. So it is kind of helpful that we've just worked out time difference. Information needs to be sent. That's why it's the hardest part of the question. The whole point of the optical fibers is the information needs to be sent with a minimum gap in time of that time difference we just calculated, because we don't want those two extremes of the pulses, the meridional ray and the one that's going down the middle of the fiber, to interfere. So the absolute minimum gap that we need to send between pulses, is the time difference. And so for no overlap, try and calculate the maximum rate, which is the number per second. And if you've got an answer, pop it in the chat bar to hosts and panelists. So thank you, I've had one answer, possibly a few more. Yeah, and don't forget to convert to kilometers to meters. Thanks very much for sharing that with me. Good, right, well, loads of messages coming in. Thank you so much for your participation. Yes, so we are on the right track. So you can see along the way, a few people made some mistakes there, but as long as you are showing you're working, you're going to pick up some marks if it's along the right tracks along the way. So always show every single step. Do not dive to the calculator. The only step you should be using in the calculator at this point is this one. So the maximum rate, so the number per second, is about 75 million per second. So well done, last few people, excellent. And if you didn't quite get that yet, you can rewatch this video later. Well, maybe not later, not today, another day, and you can have a go at the question again, okay? Because sometimes it's hard when we're working online. You might want to work at your own pace. So I'm talking as well a lot. Okay, so final question for today. We'll see how far we get. And you're going to need to draw this diagram out. So have a good read. Talking about a particle detector, not director. And remember, if you've got any questions, put them in the Q&A. Okay, in about 30 seconds or so, I'll answer some of the questions about the previous question, but I do want you to start with making a sketch of that diagram and drawing out key information that you need. Okay, so if you want to carry on that question, you're happy with the previous one, then do. It's all in the pack as well, that's been shared by Kat. But just going back to that previous question, the square wave is describing how the information will be sent, and digital information is sent essentially as pulse, well, in this situation as pulses of light. So when a ray of light is sent, that's a 1, and when it's not, it's a 0. But we don't want those rays of light, because they are light. Light can interfere. That is a light property that you learn in year 12. We don't want those light rays to interfere. From the previous diagram, we don't want them to interfere or overlap, because there'll be interference, destructive interference, constructive interference. That's going to mess up our signal. You're not going to get the information that you sent at the beginning of the optical fiber. So that's why it matters that it's a square wave of 1s and 0s. And if you know the time difference, so the meridional ray and the one in the center of the optical fiber are the two most extreme versions of the rays that can be sent in that optical fiber. That's probably the best way to think about it. So that's why we're basing our calculations around those two rays. Okay, so back to this diagram again. But the rays aren't the same. The rays are what then are represented in digital signal. Sorry, I keep pointing to my screen instead of here, as the 1s and the 0s. So that's how the information is sent in reality, if we look at it as a digital signal. And the 0s are the gaps between the signals. But you can only have the signal as long as the gap, because it's a square wave, so that shows the shape. So that gap in time difference has to basically be this, the time difference between those two rays is what's the important information. And that gap then decides the rate. Okay, so you need that gap to decide the rate between of the rate of how often pulses can be sent. Because the ones we've used in the question are the most extreme two versions. That's probably the best way to think about it. And so we have this, the gap and the signal will be the same length, because it's a square pulse. Okay, so back to this question. Put any other questions in the Q&A. So I'm just going to say, for starters, that all of these angles are not alpha. Okay, so just double check that. Okay, and then draw your own ray diagram. We know the angle A up here is alpha, so that's important information. And so I'll label that straight onto my diagram, or maybe make a list, but it has to be really, really careful. Then what I'm going to do next is, because I know that total internal reflection is happening here. Sorry, it's not total internal reflection. These are actually two plane mirrors. Because it's a mirror, it's even easier to identify it. We know that because we're working along a straight line of this angle A must be equivalent to this angle B, because I'd have my angles of incident, angles of reflection, along this normal. But I know that angle A must equal angle B. So A and B are definitely alpha. Those are the two most straightforward ones to solve. But next, I'm going to look at a specific part of the diagram. So I'm going to look at this middle triangle here. I'm just taking this triangle here, just one part at a time. And I would redraw that one section. Good, so Remy, fantastic. Yeah, that's all correct. Yeah, Elliot, well done. So we then need to use the geometry of this triangle. So use simple geometry rules, such as angle rules for similar angles and angles in a triangle adding up to 180 degrees, things like that. So a bit of a hint. Keep the answers coming. Okay, so here we've got angles along a straight line. So the angle that I'm pointing to in green must be equivalent to this, because I've got 180 degrees along that straight. Oh, sorry, I've used actually angles in a triangle there. So I've got 180 degrees in this triangle. I know I'm trying to find E, and I already know that B is alpha. So this angle with the arrow is equivalent to this. And so along the straight line, I'd have this. You might use a different route, but this is one of the ones you can use. Then I'm going to look at this part of the diagram. Just taking one part at a time. I know I'm putting them all over the page. So again, try and use your rules for triangles. Ali, just check E and C and D. Just check E and C and D. I can't check everyone's answers, but thanks for sending them in to host and panelists. Amina, you're close. Sorry, Anima, I think it is. You're close, but not quite. Alice, that's excellent. Well done. Yeah, lots of answers coming. Well done. Henry, that looks correct. So the next part, look at that triangle, and we're going to use the idea that all the angles in that triangle add up to 180 degrees. But we don't necessarily know this angle here, but we do know, so don't worry about this random line here at the moment, this line of reflection. It's more interesting to look at this, where my laser pointer is. So in this triangle, I've got 2 alpha plus D plus 180 degrees minus E, because I know that this, we must have angles along the straight line. So whatever the angle is in the triangle is 180 degrees minus E. And that gives me another statement. So I'm going to be using some substitution. So can you substitute equation 2 that I've numbered into equation 1? Yep, Yitian, excellent, well done. You can look ahead in the pack, anyone that thinks they've finished, but do keep checking your answers. So you should get that C equals 3 alpha. C equals 3 alpha. So because C equals 3 alpha, just come back to this part of your diagram. Again, we've got reflection from this plane mirror. So if C equals 3 alpha, you know what D is. So D is equal to 3 alpha as well. And I'll go quite quickly now. So hopefully you're seeing the idea. And we can substitute that into equation 2. And we get that E is 5 alpha. So there we've got all of our angles from the diagram in terms of alpha. Yeah, Frederick, well done. So I'll move on now just to try the last part of the question. I'm not sure we will move on to part C. Oh, we might move on to part C. So have a go. Think about what will happen after several reflections of the light down the mirror funnel. You can see that I tried to start sketching it on already. So the ray, the purple line, is a bit dodgy here, will next go to the top plane mirror in this particle detector. Okay, so plane is just another word also for flat in this situation, so these flat mirrors. So have a go at thinking about what's going to happen after several reflections, what will happen to the light after several reflections. Then have a go at C. You're given a value for alpha. So what will eventually happen, and it doesn't really matter if I know whether it happens there or whether it happens further along, but just from experience and logic, the rays will reflect back out of the plane mirrors eventually, because eventually one of them will reach one of the plane mirrors at an angle of 90 degrees, so along the normal, and that will reflect right back along the path it just arrived on. So it doesn't matter whether this is the right point, we're just sketching it to help us think about it. And then it will also go back out eventually of the mirror funnel. So eventually the light will reflect back out. We don't need to have any values on that at the moment, but that is what will happen, whether it happens there or whether it happens further along. Yep, so Cyan, well done. The light will come back out eventually. And yeah, it's just 2 sentences. Few people asking how long that question is meant to be. The answers to A, just one more time because you will need them, are that we already had that A was alpha. We have here that C was 3 alpha, so D must be 3 alpha as well. and E was 5 alpha. But please remember to put questions in the Q&A so I don't miss them. So using those, you'll need to use the alpha is 10 degrees. I have to make this our last question. See if you can work out the total number of reflections between the mirrors that will be made by a beam of light. Okay, so I've had 2 answers for part C so far. One of them is correct. So Yitian, well done. No one else in the chat to host and panelists has said the correct answer yet. So no one else said the correct answer yet. I'm keeping an eye. Nope, no one yet. It's a hard one. Lewis, you're quite close, not quite. Okay, so I'll put the next step. Oh, if it works. So we knew this from the last part of the question. We know that alpha is 10 degrees. So you should have got this so far for E. And then we can see that there's going to be a trend. So using what we said in B, eventually it will reflect back out. And I did mention about this already. This is how we know. So looking at that, you have a sequence or pattern really in that data. A is 10, C is 30, E is 50. You can make a prediction really that the 4th reflection that's not drawn there will be 70 degrees. And so you can make a prediction again. Yep, Freddie, you've got that correct. Sorry, I have kind of lost track of the chat right now. Reem, I think it's Rima, I can't see your whole name. That is correct, well done. A few people, yeah, lots of people giving answers, not quite correct. So the next one is 90 degrees. Now remember, when a ray hits any surface, so where my laser pointer is now at 90 degrees, it's just going to reflect back along the path it just came on. So like this ray here that I drew, if it hits the surface at 90 degrees to the surface or along the normal, it's going to reflect straight back along its path. So the next angle of reflection should be 70 degrees. And so you should actually end up, lots of people got 8 reflections. Some people got 10. The answer is actually 9. Yeah, Eliza and Alice just realized, George, well done. So you only have 1 reflection of 90 degrees because that will take the ray back down along its path. And so you'll have exactly the same reflections on the way back out again in that setup. In the pack, there's another part of the question, but so that Kat can speak to you all again, that's the last one there. There's one question in Q&A and I'll try and type an answer. But yeah, we've used sequences there. So not as complicated probably as it first seemed. Well done, everyone. Thank you so much for your participation. Those 2 questions are in the pack. But well done and a huge good luck for your PATs. Remember, try every question and show you're working. Don't get bogged down in anything. Thank you. So I'll hand back over to Kat now. She wants to say any last words to you.
Hello, thank you so much, Rachel. And I unashamedly admit optics is one of my favourite parts of physics. So I have really enjoyed this evening. Slightly controversial opinion. I know lots of people who don't share my deep love of optics, but I'm certainly a big fan. We have 5 minutes left. So if anyone has any specific PAT-related questions, do feel free to pop them in the Q&A just now. If you don't have any questions, feel free to leave the session. I will share the video tomorrow morning, but we do have a few more minutes left. So if anyone wants to share anything in that Q&A, do feel free. We'll see if they come through. And Rachel, would you mind stopping sharing your screen once you're ready? Amazing. Now you can see us both. Oh, start time on the 20th. I'm afraid you have absolutely gone straight in with the question I do not know the full answer to. I would suggest your school or your test centre will get back to you with that information, and it will probably also be on the website pretty early. I'm afraid off the top of my head, that is not one that I have straight away. Lewis, in terms of a PDF with all the definitions, or do we need to look through different exam boards? We do not provide a very detailed syllabus. So the syllabus is available on our website, and I share that link in every single email, but we do not have a list of all of the definitions. You'd need to look through the syllabus and then find them yourself doing your own revision. That one is there. And then, do we get to know our PAT score before the interview? Your PAT score will be used as part of shortlisting, so you will have an idea of how you've done. Again, if you have a look on the page about how you get your scores, that will give you more detailed information on that one. What else have I got in the Q&A? So I've done the PDF, done PAT scores. Morning or afternoon. Again, Matthew, I'm afraid I just don't have that information straight off the top of my head. So I can try and answer it tomorrow morning when I send the email through to you guys. In terms of, is PAT marking more lenient than typical A-level marking, for example, with definitions? So lenient's probably not the right word here. Your answer will be considered on its own merit. So every answer is going to be taken in terms of how it relates to the question and what that indicates about your ability in that subject. So it is worth noticing as well that every PAT is marked by the subject specialists you are applying for. So although the PAT is shared, I said right at the start, it's the test that you need for physics, physics and philosophy, engineering and materials science. If you are applying to physics, your PAT will be marked by physicists. If you're applying to engineering, your PAT test will be marked by engineers. And so lenient is not the right word. I couldn't really say, but your answers will be marked on their own merit. And I hope that helps you with that. Do you think further maths is a must? We don't require further maths. It is very useful. So it really depends on your own reasons for not taking further maths, I would say. Working down my list, what's the criteria for using a different calculator? If that you mean bringing in a calculator other than the online calculator, you would only be allowed that if it was a specific access arrangement. So if you had a reason which your school have evidence of for you not being able to use the online calculator, otherwise, no, we are not allowing other calculators into the test. A lot of people seem to be quite worried, saying that it's quite time pressured with the online calculator. I can only emphasize that everyone is sitting the same paper with the same calculator, but also the paper is not particularly calculator heavy. So as Rachel was saying in quite a few of her answers, where you're only using the calculator at the end, you probably won't be spending much time with the calculator. And you've got plenty of time to get used to it. So really the calculator is not a significant issue there. I know it seems really scary that it's a big change, but please trust us, it's not as scary an issue as it seems. And then working down, can quantify the percentage of importance relative to the other aspect. No, there is not a fixed percentage that your PAT makes up 30% of our consideration or makes up 60% of our consideration. Every application is considered on its individual merits, and your PAT score is part of that. So I cannot give you a fixed percentage. Got somebody saying they've read the admissions reports, often as a mark for a guaranteed interview. Below this mark, it says people with contextual information are considered. What exactly constitutes these criteria? So those contextual pieces of information might be things like if you go to a school where your teachers have absolutely no experience of bringing you to those, or if you've had extenuating circumstances. So again, there's not a really specific, this is contextual information. This is more looking at your application in a really overall way and considering. And that is why there is not a specific, yes, this mark will get you something. Are the grade boundaries on engineering for the PAT slightly lower? They will be different rather than specifically slightly lower. So if you have a look on the engineering site, you'll be able to get those pieces of information. Sorry, I know I'm rattling through these, trying to get to the last few now that we've passed 8 o'clock. So on the website, it says to register with the email you signed to sign up to UCAS. I am honestly not particularly sure. I would get in touch with the test registering people rather than me for that one. I'm afraid I'm just not technically in the know of what the behind the scenes software would look like for that registration. I'm sure it's fine if you still are registered for the PAT, but I think it means that your scores go through automatically, which is why they ask you for that. So just get in touch with our admissions team. There's loads of links on the FAQ page. You'll be able to find that or give them a ring and they'll be able to check that out for you. In terms of where we can test out the calculator, I'll send a link tomorrow, but it's on your online preparation page. You simply click through, try the online test here, start the test, and then there's a link for the online calculator within that. And you can have it up to use other questions as well, which is what I'd recommend. Don't just use it for this one practice test. Use that as your calculator for the next couple of weeks. Get used to it. More questions, guaranteed PAT score for interview. Have a look through the admissions report. We do have sort of a guidance for it, but every application is taken individually, as I've always said. Topic list doesn't say decay, even though they're decay questions. Please bear in mind the PAT syllabus changed in 2018, so we may well be using example questions to illustrate problem solving, which are no longer on the syllabus. That's why you need to have a look on the syllabus. Selecting a college for engineering. Remy, if you have a look at some of our general admissions pages, you should be able to get answers for that. Anything I don't answer that you still want more information, do feel free to drop me an email and I'll be able to answer a few of these in more detail. And then I've got one last one on the admission statistics. It mentions contextual GCSE scores. Okay, so that's quite a personalized question that I've got as my last one, again about contextual scores. I'm going to round up now. What I'd say is I've tried to get through some of these questions. If I have not answered your question, please do feel free to drop me an email. So you will all get an email tomorrow morning giving you the link to this recording, setting you the problems for next week, and all those things. Please drop me an email, ask these questions. Even if it takes me a week or so, I will answer every single one of them and get back to you. So if I haven't answered anything, or if you have quite a specific question that might not be one particularly relevant to this situation, feel free, send me an email and I will get to them. Thank you so much, everybody. I will see you next week. I hope to have loads of emails in my inbox ready for me to open tomorrow morning. I will end our meeting now. Thank you so much, everyone. I will speak to you soon. Goodbye for now, everyone.